everyone. In this video session, I am going to discuss about the instrumentation of NMR and the type of NMR spectroscopy. So let's start with the instrumentation of NMR. So this is the block diagram for NMR. It has a strong magnet with a homogeneous field, and the strength of its field can be varied continuously and precisely over a small range with the help of the sweep generator. Second part is a radio frequency oscillator to generate the RF wave. Third part is radio frequency receiver and detector to detect the RF after passing through the NMR sample. Part is a recorder, calibrator and integrator to provide the NMR spectrum. Other important part is the sample holder. Sample holder holds the NMR tube and it spins the NMR tube to increase the homogeneity of the magnetic field on the sample and keeps the sample in the proper position with respect to the main magnetic field. Now magnet, it must be strong, stable and produce a homogeneous field. Homogeneous means the field does not vary in strength or direction from point to point over the space occupied by the sample. Now there are two components of a magnet. First is superconducting magnet. It is made up of superconducting NBSN or SP titanium wire, and the magnet is submerged in liquid helium for providing the sufficient cooling. The magnet and the liquid helium reservoir are encased in a liquid nitrogen reservoir to decrease the evaporative loss of more expensive liquid helium. Second component of magnet is SIM coils. SIM coils are used for making magnetic field homogeneous provided by the magnets. Now for loading the sample in an NMR instrument, we use a sample tube, which is also known as NMR sample tube. And this NMR sample tube must be transparent to RF radiation, it must be durable and chemically inert. It can be made by glass or Pyrex and with sturdy, practical and cheaper material. They are usually about 6 to 7 inch long and 1/8 inch in diameter and having a plastic cap. Now how to prepare the sample for NMR study? For preparing the sample, we have to dissolve 2 to 5 mg amount of sample in a 0.5 ml of deuterated solvent and add it to a NMR tube. The solvent used to dissolve the sample should contain no protons, be expensive, low boiling and inert. And the common solvent fulfill this condition are like CDCl3, deuterated acetone, deuterated methanol, deuterated water, etc. But now question arises here, why we use deuterium solvent while deuterium is also an NMR active nuclei and it must show a NMR signal in the spectrum. But under the applied magnetic field, the gap between energy states for deuterium is different than proton. So it resonates at different radio frequency than proton under the same field. As a result, it does not appear when we go for proton NMR. Now type of NMR spectroscopy, first is continuous wave and second is Fourier transform NMR spectroscopy. So let's start with continuous wave. The common method for obtaining NMR spectra is to irradiate the sample with a constant radio frequency while changing the applied magnetic field. However, the sweeping or changing of magnetic field is not the easy task. So alternatively, NMR spectrometers operate at a constant magnetic field while the radio frequency is varied. Means we are sweeping the radio frequency while keeping the magnetic field constant. So both the methods give the same NMR spectrum, and this commonly used technique is called continuous wave NMR spectroscopy. Second type is Fourier transform. In this technique, under the constant magnetic field, the sample is irradiated with an intense pulse of RF in the desired range at once. All the nuclei under study absorb at their individual frequencies and are flipped to their higher energy spin states, that is -1/2 spin states, and gives an interferogram called free induction decay. So this is free induction decay. So this free induction decay cannot be interpreted directly to get the structure of organic molecules. The free induction decay spectrum is converted into ordinary frequency domain spectrum by performing a mathematical operation known as Fourier transformation. and this technique is called pulse Fourier transform nuclear magnetic resonance or FT-NMR spectroscopy. Now we'll see what is free induction decay. When the RF pulse is discontinued, the excited nuclei begin to lose their excited energy and return to their original spin state, that is spin state plus 1/2, and they get relaxed. As each excited nucleus relaxes, it emits electromagnetic radiation, and this emission is called a free induction decay signal. So this is free induction decay signal. And since the molecule contains many different nuclei, many different frequencies of electromagnetic radiation are emitted, and the FID is superimposed combination of all the frequency emitted, and it can be quite complex. So we usually extract the individual frequencies due to different nuclei by using a computer and a mathematical method to convert it into an ordinary frequency domain spectrum, which is called a free transform analysis. And we use this ordinary frequency domain spectrum to get the structure of organic molecule. So finally, I would like to acknowledge these books, and thank you very much.